Alright guys, third and final video on pseudo-random number generators, and today we're gonna... oh no, I deleted our Instagram handle. Oh no, that's so bad. Okay, so pseudo-random number generators, we saw what they are in 2 videos ago, how they work, the entropy, the entropy was before, but we saw how pseudo-random number generators work, what's an entropy pool, how they work in general. Then in the last video we saw some real-world application of pseudo-random number generators. And now, to conclude chapter 2, the chapter that talks about randomness, we are going to talk about when things go wrong. Okay, when things go wrong. Perfect. So, when do things go wrong? The author gives four examples, which are pretty cool. And yeah, let's go through them. So number one is things can go wrong when you have a 4 entropy source. Okay? Makes sense, right? If we don't have a good entropy source, then we're gonna end up with a weak pseudo-random number generators, and so attackers will be able to exploit this flaw to guess the next random number, so de-randomize the process. And so for this example, the author gives an example. Voila, I like to write EX as examples. About the 1996 SSL implementation of Netscape browser. Okay, and what happened there is that there was a... I'm just gonna write the line of code that did this. CKLPR bit seconds. Okay, this basically, we have a variable b. Oh boy, guys, don't worry, the new markers are coming, eh? New black marker are coming. So value of b, which is given by MKL or CPR. MKL CPR. MKL CPR. Okay, and this function has PID, per seconds. And then plus PPID. Okay, now the problem with this line of code in here was that there's an overlap of 3 bits, and so instead of being 15 it's 12. I haven't exactly quite catch the exact problem, but the author basically makes a point that process ID and seconds are guessable by an attacker, and the parent ID. So what happens is that from a function that it's supposed to generate a 128-bit seed, by doing the calculation of, you know, how many you try to guess, if once you guess the seconds, then you have 10 to the 6 chances to guess the milliseconds, so still very doable number for computers. But the point is that we're reducing we're having an entropy of 47 bits. Come on, don't die. Okay, 47 bits of entropy instead of 128 bits, right? If we want to have a 128-bit key, we better have a 128-bit entropy. We saw in the video of entropy how to calculate it for X bits of randomness. And so, okay, low GoPro battery. Oh boy. Let me stop and continue, charge the camera for a little bit and continue. All right, be right back. Alright guys, in the meantime that the camera charges for a little bit, well, first of all I got a battery for the GoPro, and then next since I felt like I wasn't explaining you the bug really well, I actually went and found the exact source that was explaining this bug, and let's go through it together. So what's happening is that there was a cryptographic function that would generate a seed, okay, a 128B seed, okay. But the problem is that since this function right here and MD5 are fixed unkeyed algorithms, right, that everybody can use, the seed generation depends only on the values of A and B, okay, so A and B, right? And the values of A and B depend on what? Depend on the time of the day, so the seconds and the microseconds, the process ID, PID, right here defined, and the parent process ID, right here, okay? So if an adversary can predict these three values, again, process ID and parent process ID can be predicted by looking at the, the system options. And then seconds and microseconds, again, seconds of the day, they can be guessed on, to the order of 10 to the 6 something, especially the microseconds. Microseconds can get guessed to the, you only have 10 to the 6 tries to figure out the total number of microseconds in a timestamp. So, so again, an adversary that can predict these three values, so microseconds, process ID, time of the day, so microseconds, seconds, process ID and parent process ID, can then apply MD5 and this function, MKLCPR, and basically compute and get the exact seed that the software would generate. And therefore, what you have? You have the seed, and then you have all the future random numbers that are generated. You have you're gonna get a hold of the cryptographic keys used by the application. So big problem here. And this was the line that I was referring about. This is when things go wrong. All right, so I'm gonna wait a little bit more, the camera charges, and then let's go back to the board to see the other three instances of when things went wrong with, when things can go wrong with pseudo-random number generators. All right, see you on the board. All right, we're back. The battery of the camera is juiced up, and so we can continue. All right, so I'm glad I could make the little parenthesis and explain exactly how does the poor entropy source, the bug in Netscape worked. Again, the value of A was based on microseconds, and the value of B is based on process ID, seconds, and parent process ID. So guessing the time of the day, so the seconds and the microseconds, allowed you to get the value of A and B, and then you could just run through the rest of the code and figure out the seed, right? Attackers should not have access to the seed at all. Next thing that can go wrong, let me separate them. Second one is insufficient entropy at boot time. So even here, so it's another type of poor entropy, kind of like sufficient P at boot time. Boot time when the computer starts. And so what's happened there? This is very cool. In 2012, some researchers literally scanned the whole internet and harvested a bunch of public keys and SSL certificates, right? and public keys, SSL certs, okay? These things were harvested from all over the internet by researchers, right? By many servers and assets. And so what they found is that many systems had the same or similar public keys, for example. I'm just going to keep the example of public keys, right? So many systems had the same or similar public keys, right? This is the internet, all over the internet right here. Many systems had the same or similar public keys. That's what the researchers found. But how is that possible? Well, it turns out that those public keys, especially, you know, all these public keys that looked similar and the same, were all generated too early at boot time. So why? Generated early at boot time. Why generating the keys early at boot time is a bad idea and resulted in a lot of same or similar public keys? Well, because the entropy pool of the operating system pseudo-random number generator was not ready yet, was not filled up with entropy yet, right? And so there wasn't enough entropy collected by the operating system and in the entropy pools. And so the algorithm of public key generation ran, and instead of getting really instead of really getting pseudo-random bits, it was getting the same bits that were maybe generated by the same operating system seed, right? By the same seed of the initial seed of the pseudo-random number generator. So big problem, all right? Big problem, because then again, many keys, easy to guess. You guys can see the big problem there. So very interesting, and again, it shows how the entropy pool is, how the entropy pool works, and how having insufficient entropy is bad, especially at boot time. Obviously, this was fixed, and when I mean that they had similar public keys, I mean that they shared the same prime factors of key generation. So that means that yes, they started from the same seed and a little bit of entropy. They had only had a little bit of entropy of difference, a little bit of entropy injected between them to make them two different. Okay, so this was a very interesting episode of how things can go wrong in pseudo-random number generators. Third one, we kind of talked about this before, but I'm just gonna go over it a little bit more, is using non-cryptographical pseudo-random number generators. Okay, now this there was a very specific instance of this, which was MediaWiki. MediaWiki is the system that manages all the multimedia in Wikipedia, and MediaWiki was basically using a how can I say, was using randomness, right, to generate security tokens, temporary passwords, right? All these things were using randomness, pseudo-random number generators. What's the problem? The problem is that the randomness that MediaWiki was used to do all this thing came from, so rand came from the Mersenne twister. Okay, so they used MT, the Mersenne twister, to sample those random bits, And so this is a huge problem because the Mersenne twister is a non-cryptographical pseudorandom number generator. And so what it means is that the attackers could just obtain a couple of tokens, and from there they could actually guess the whole sequence of the other new tokens generated from that point forward. So guys, never use a non-cryptographical pseudorandom number generator for cryptographic application. If you have to create temporary passwords, if you have to create, you know, things that need high entropy and safety. And now the fourth instance of things that went wrong was with Cryptocat. Cryptocat was a messaging app that allowed you to send safe encrypted messages between people, so ouch. And the problem there was that Cryptocat had a, okay, this is called sampling bug. With randomness, okay? And so what does that mean? Basically means, I'm gonna just write it in simpler words, is a strong pseudo-random number generator that still produces a biased distribution. How is this possible? So in Netcat, there was a function that generated a string of uniform decimal numbers. So there was a function that had to create a random string of 0, 5, 4, 9, 3, 1, 7, 3, 5, 1. So it did this by taking a string, a series of bytes, and doing modulo 10. Okay. The problem is that doing any number between 0 and 255 modulo 10 does not yield a uniform distribution of decimal numbers. Okay, so yeah, they were using, you know, good pseudo-random number generators, but then in their code they were basically running all of their bits, all of their all of their bits and values through modulo 10, which did not absolutely yield a uniform distribution. Okay, and so they solved this, and they wrote more code that and by what I mean by uniform distribution is that there's not an equal number of values of 0 to 9 values, right? There needs to be an equal, more or less an equal amount of zeros, an equal amount of ones, an equal amount of twos and threes, etc. But it wasn't the case if you do this, okay? And so what they did, they wrote additional code that it doesn't just take all of them, all of these, but it only takes the multiples of 10, and then takes the the module of those, and it discards the other. And again, and they almost fixed, but then they had just a little. Let me see if I can just quote it really fast. Where was it? Sampling bug. Let me see. They had a right here less than or equal to, which unfortunately gave an off by 1 error. So if they had a if x is 0, if x is 0 less than or equal to 250, okay, then you would do O plus equal. Oh, this is, yeah, O, so this is a letter O plus equals to x index 0 This is a 0 modulo 10. Okay, problem here. There should not be, this part of the code they wrote to fix this, there should have not been an equal, because again, we give another multiple of 0. It should be like this. This fixes the problem of not creating a uniform distribution. Again, I might not have not explained this super good, but the gist of it is that you use everything correctly, right? You use a very good source of randomness, a good pseudo-random number generator, but then you might write code because maybe you need to produce some particular string or something, but then you might mess everything up by writing some code that really does not transform what is a uniform distribution, so a string of random bits, into a non-uniform distribution, in this case by using modulo, okay? And so, very interesting, this is the sampling bug with strong randomness, okay? So, let me see. And that's it, this concludes the chapter 2 of randomness, okay? We'll be talking about randomness a lot, obviously, because randomness, again, is part of, is one of the foundations of cryptography. Yeah, I mean, there's a lot more. We just scratched the surface. The author really tells us that we've been just scratching the surface of randomness, because, you know, there's a lot more about the theory of randomness. There is different entropy notions, randomness extraction, power of randomization and de-randomization in complexity theory, and so there's a bunch more stuff. And the author suggests to read a paper called Cryptanalytic Attacks on Pseudo-Random Number Generators by Kelsey, Schneider, Wagner, and Hall. This must be, I'm gonna give it a read tonight when I'm chilling at home. And then yeah, it just it encourages you to look at some implementation of these pseudo-random number generators in your favorite language. And this concludes again the chapter on randomness. I hope you enjoyed. I really enjoyed about learning about randomness. It's really cool now when I see anything that deals with cryptography. I always think about, you know, the randomness source and everything. So really happy. I'm really enjoying making these videos and learning about crypto. Please leave me comments with good or bad feedback. I really need to know what am I doing, if I'm doing good or bad. Please don't give feedback. And then nothing, if you like this, support my channel, my time by liking and subscribing. And guys, I'll see you next time for chapter 3, cryptographic security. Have a good night, have a good day, and see you next time. Bye bye.